everyone, today we are going to learn about minimum spanning trees. Chapter 9, Section 4. The section summary we are going to learn about only Prim's algorithm or greedy algorithm. Section objectives include only one objective, which is giving a weighted graph and a vertex. You will be able to construct a minimum spanning tree using Prim's algorithm. Minimum spanning trees. The definition, let G be a weighted graph. A minimal spanning tree of G is a spanning tree of G with a minimum weight. So in the previous section, we have learned about only how to construct spanning tree. But if we have a weighted graph, how to construct the minimum spanning tree of it. So we have this example here. Find the minimum spanning tree of this simple graph. G is the graph T. And you can notice that you can find a simple path between any two given nodes in T graph, which is the spanning or the minimum spanning tree of this version of the graph. But the question here, do you think that the T, which is the spanning tree, is the minimum spanning tree here? Can you find another minimum spanning tree using, for example, the travel person, the sail travel person, the sail travel problem? There's no person. Okay, so you can find, I'm sure that you can find multiple spanning tree, but how, the question here, how to find the minimum spanning tree? Let's discover that. So to find it, we can use Prim's algorithm, or another name for it, it's the greedy algorithm. This algorithm builds a tree by iteratively adding edges until a minimum spanning tree is obtained. The algorithm begins with a single vertex, which is the root, then at iteration, it's asked to the current tree a minimum weight edge. Pay attention, it's an edge. We are dealing with the edges. That does not complete or cause a cycle. So this is the algorithm. It's a long algorithm, but we are going to learn it by using an example. Example for that, use Prim's algorithm to find the minimum spanning tree for this graph. Assume the start vertex S here is 1. So let's see, go. Okay, so first the root vertex is given, which is 1 here. Okay. So how to construct the minimal or the minimum spanning tree from a graph G, and the solution here it's given. So you can see this is the minimal spanning tree, and there is no a simple circuit. You can choose any two nodes in this graph or in this spanning tree, and you can find the simple path between any two chosen nodes. But the question now, how to use Prim's algorithm to construct or to find the minimum spanning tree in the graph G. So first, we have the vertex 1 is given here. So let's discover, or let's construct, first let's draw the spanning tree with only 1. So here, I'm going to redraw this graph. So now we have only 1. Okay, let's start with 1. And now you need to consider, you need to construct a table of 2 columns, edge and weight. So for the first one, we are here at vertex 1. You need to list all the edges that are incident to 1. So what we have here 1 and 2, we have 1 and 3, and we have 1 and 5. So 1 and 2, the weight of the edge 1 and 2 is 4. The weight of edge 1 and 3 is 2. And the weight of edge 1 and 5 is 3. Now, to choose the next vertex, we need to find the minimum weight among these numbers, which is 2. So in this case, let's add 3 and let's add the weight. Okay. So we have here 3. Okay, so now we have only 2 nodes, which is 1 and 3 in the in our spanning tree. But one condition in the spanning tree, we need to cover all the vertices in the given graph. So now we have discovered only 1 and 3. In the next step, we need to add the high weights of the edges that are incident to the first to the previous node, which is 1 and 2 and 1 and 5. We need to add them here. Okay, but this one will be removed from the next step. But in the next step, we need to discover all the edges that are incident to 3, because we added 3 to our spanning tree. So what are all the edges that are incident from 3 or to 3? They are 3 and 4, 3 and 5, and 3 and 6, right? So we have 3 and 4, 3 and 5, 3 and 6, along with the previous unvisited edges. Okay, so test all the weights that we have here. So we have 4, 3, 1, 6, and 3. What is the minimum weight? Here it's 1, right? And it's the edge that connects 3 to 4. So let's add this edge, right? So we need to follow the same construction of the graph. So we have 1, 2, 3, and we have 4 here, right? And what's the weight here? It's 1. Okay, and let's remove this edge, okay, from the second step. And the third step, again, we need to add the n discovered already listed edges, okay? And so we have here 3, 5, 3, 6. Okay, and this example from your book, but I don't want you to consider this one. This is wrong. Okay, so now we are at vertex 4. So let's discover all, or let's include all the edges that are incident to 4. So what we have 1, 2, 1, 5, 3, 3, 5, and what we also 3, 6. Sorry, this goes to 3, 6, not this one. Okay, and let's add the edges that are incident to 4. So what we have, okay, it's here. Okay, we have 4 and 2, right? We have here 4 and 2, which is 5, and we have 4 and 6, which is 6. Now let's choose, okay, let me remove this one. Let's choose the minimum weight again. So what we have here, we have 3 appears 2 times. So which one should I choose? We choose always the first one. Okay, so this one, added. Okay, so what we have here from 1 to 5. Okay, from 1 to 5, and what's the weight? It's 3. Okay, so we have, or we should remove, we must remove this edge. And the thing I need to mention here, the edge here must have at least one uh, undiscovered or not added vertex. If we have, for example, why I'm deleting these nodes, because 1 and 5, both of them are now in the spanning tree. 1 and 3, both of them are in the spanning tree. So we need to have at least one undiscovered or visited node. Okay, so now we are at 5 vertex. So again, let's, in the next step, or in the next iteration, let's add the listed and visited, or with high weight, from the previous step to the next sorry, step. So what we have here, 4 and 2. This is 4 and 2. Okay, this is here 4 and 2, which is 5. Okay, so 1 and 2, we have 3 and 5. Why it's removed? You can see here, because 3 and 5, both of them now in the spanning tree, our spanning tree. So both of them are here. We cannot have it in our table. We cannot have an edge that has two already visited nodes. Okay, so we have 3 and 6 here, 4 and 6, and now because we are at 5, so let's add all the edges that are incident to 5 and at the same time unvisited, okay, or not visited. So 5 and 1 is already visited. How about 5 and it's already there? And how about 5 and 6? So we added here 5 and 6. So now let's test, or let's choose the minimum weight. The minimum weight is 2, which is 5 and 6. And let's remove this edge from the table. So here we have, let's have the same construction here. So we have 5, the edge 5 and 6 with the weight of 2. Okay, so let's remove this one. Okay, now let's test if we have 2 visited vertices in every edge that is listed here. So 1 and 2, 2 is not discovered, so we need to keep it. How about 3 and 6? 3 and 6, both of them visited. How about 4 and 2? So we have, okay, so we have this one. Okay, 4 and 2, 2 is not visited. Okay, so we need to include them. So this is 4 and this is 2. Okay, this is for the next iteration, or for the next constructed table. And this one and this one should be deleted. And how about 4 and 6? 4 and 6, both of them in the table, or I'm sorry, in the span tree. So we need at least, we need to have an edge that has only one unvisited node. Okay, so in the last table we have the edge that connects 1 to 2 and 4 to 2. Which one is or what is the minimum weight here? It's 4, which is 1 and 2. Okay, 1 and 2 with the minimal weight, or the minimum weight is 4. Okay, now if we have the next step, we need to construct a table. Okay, but this one, it will be gone, and then we have the next table. It has, so this is edge and this is the weight. We have only this vertex is left. So we have 4 and 2 with the minimum weight is 5. But do you think it's correct? We cannot include it because 4 and 2 of them are already discovered, or have been visited. So there is no next step. We have visited all the vertices here, and we have used a Prim's algorithm to construct the minimum weight of the spanning tree. Okay, so you have two practice problems. The first one, find the minimum spanning tree given by Prim's algorithm for the given graph. Assume the start vertex is 1. So again, from 1 you can construct a table that has two columns, edges and weights, and list all the edges that are incident to 1, and then keep repeating the same step until you covered or you have visited all the vertices and constructing the minimum spanning tree. Submit your solution again to get the Excel credit before the end of the day. The second question, the same question, but with different graph, and also the roots or the start vertex is 1.